Hi, I'm Dane Quinn. I'm a professor of mechanical engineering at the University of Akron, and I would like to welcome you to our video lectures for Kinematics of Machines. So let's go ahead and jump right in. This class is about motion and mechanisms, and in particular the kinematics of machines. So what's a machine? Well, it's a combination of objects arranged to do work. So the idea behind a machine is that it's a collection of things, right? Simple, complex things, and in particular it has a goal. It is arranged and designed and put together so that it accomplishes work. Remember what work is. It's force dot displacement. So that concept has ideas of force and motion. So in particular, we're going to be looking at mechanisms in this class. So what's a mechanism? Well, it's an assemblage of objects or bodies connected by movable joints and these are also constraints to form a closed kinematic chain. So we'll talk some more about this and the ideas behind kinematic chains later. But in particular, it has the purpose of transforming motion. So again, this is a class on kinematics of machines. Right, so we'll be looking at mechanisms, and we'll be trying to analyze and design mechanisms to accomplish specific goals in terms of their motion. So when we talk about engineering design, and in particular the design of machines and mechanisms, I like to think about this as broken up into sort of three steps. One is the synthesis step. So the idea behind the synthesis is that we're going to come up with an idea of how we want to obtain our goal. With what kind of mechanism we want to use, just the general idea of how we want to approach solving the problem. Then the design aspect comes in. So the design aspect is a little more detailed. It's picking the specific components, maybe link lengths, radii, the overall configuration of the mechanism that we want to design. And then the last step is analysis. So that's the application of scientific techniques, and they could be mathematical. You could run experimental trials, you could do computational work, but we'll apply those techniques to examine the performance of the design that we've come up with. So we want to ask, how well does our design meet the goals? So in particular in this class, we're really going to be looking at the last two, and mostly in the analysis section. So we will focus on the design, and in particular the analysis of planar mechanisms. So planar mechanisms are mechanisms that exist in the plane. So you can draw their representation on a piece of paper, right? Nothing would come in or out of the paper. And all of the kinematics, right? The velocities, the accelerations could be described within the plane. We're not really going to focus on spatial mechanisms in this course. So a little bit more, right? This is kinematics. So what is kinematics? Kinematics is the study of allowable motion. Right? So what could possibly take place? And it has to be consistent with the constraints of the system. But in particular, without regard to the forces that produce that motion. So we're really not concerned with why a mechanism moves the way it does, but more how it moves. So we want to think about input motion and output motion. And that's really the objective of this class. It's to describe the kinematics of machines. So I'd like to relate input and output motions. More generally, we want to relate the motion of one component to another. So if I look at these figures, I've essentially drawn what's known as a 4-bar linkage. So here, if we look at this second picture, we have one link. So this is just a fixed bar of fixed length in light blue. We have another one in red, and they're connected with a pin. That red link is connected to a dark gray link with a pin. And then that dark gray link is again connected to the ground. So you could think about the fourth link as representing the ground. So imagine you drew a bar between these two. Right, there we have 1, 2, 3, 4 links. Right, so 1 will always be the ground, 2, 3, and 4. So now, if I think about the blue link as my input, then depending on where it is, the red and the gray links move around. Right, so if it's at 0 degrees, then the red and the gray are like shown. Here in the lighter lines, I've shown different configurations. You know, it moves up to 60 degrees, and then the red and the gray link move here, 120, 240, right? And then, you know, about 300 degrees, and then back to 0 again, right? So as this blue link spins around, this mechanism would move through all of these positions. So in this class, the real objective is to relate the configuration of these different links, in this case link 3 and 4, back to the input position of link 2. Right, so if you look and see what this does, link 2 could spin around, for example, and link 4, the gray link, would sort of rock back and forth. Right, so this would actually be sort of near its maximum position, and then as we move here, it would swing down to this sort of minimum position, and then it would return back here on the next cycle. So we'll really be focused on the configuration and the kinematics of linkages. Right. We'll look at position, and then we'll look at velocity, and then finally we'll look at acceleration. And I'll point out, and this is an important part of this class, for an ideal mechanism, and that's one that has no losses, right? So there's no friction at the joints. And also the masses are assumed to be massless, right? So we don't have to worry about inertial effects. So if it's massless and lossless, we can use the kinematics. Right, so we can use the motion to describe the forces. And this is based on concepts of work. Right? Remember, work is force dot displacement. So it seems to reason that the forces and the motion are related for a mechanism. Alright, so that's just a really quick introduction to this course in Kinematics of Machines. And next time we'll start in on some vector analysis and then really begin to look at the kinematics of linkages. Thanks a lot, and I will talk to you again. Bye.